Okay, so let's get started. Um, uh, okay, so it's lecture 26, and it's the last lecture about about differential equation, about ordinary differential equation. And the agenda for the lecture is I'm going to finish talking about a homogeneous system of first order ODE. So in the last lecture, we talked about what happens when A has real eigenvalues, but now I'll talk about what happens when you have complex eigenvalues. And I'll briefly say something about the inhomogeneous case, which refers to the same equation, but now you have some f that's not necessarily 0. So you have these are all functions of t. And then I'll finally spend quite a bit of time talking about why this is an interesting setup, why systems of first order ODE are powerful and interesting. So, so what did we do last time? Well, we ended on sort of a high note. So we proved the following theorem, which was given some system of homogeneous system of first order ODE like this in normal form. If this matrix A is diagonalizable, then the general solution is very simple, simply expressed in terms of the eigenvalues and eigenvectors. So if it's diagonalizable with, let's say, real eigenvalues, and therefore real eigenvectors. So this is an n by n real matrix. Then the general solution of this equation, which, in the background is always this linear transformation T. So that the solution of the ODE is just the functions in the kernel of this linear transformation. Then we showed that this is actually just a bunch of exponentials. Exponential functions times the corresponding eigenvectors. Okay. And I mean, the proof was, I won't repeat the proof, but the proof was this amazing fact that, if you look at functions that are parallel to the eigenvectors, this system of ODE actually just becomes a one-dimensional, first order ODE, which you can easily solve with an exponential. So, the way I've written this suggests that this is a basis for the kernel of T. But we never actually proved that these functions are linearly independent. Right? Yeah. So it seemed to have deleted my whiteboard. Just a second. I'm going to look for the see if it saved the whiteboard somewhere. Okay. Nope, didn't save the whiteboard. Okay. Okay, I'm just going to quickly write that again. Let's hope it doesn't happen again. I'm not going to write all of it, but wait a minute. Is this even being recorded?
Yes, it says it's recording.
Okay. So let's see. Does it say on my computer that it's recording? Weird. Wait a second. Ah, good. Okay. At least it's still recording. Okay. So all that stuff will be in the recording. Okay, fine. So I'm just going to quickly. Okay, what did I just say? Okay, lecture 26. So watch video for full slide, I guess. Okay. So what did we do last time? We said that if A is diagonalizable, then the general solution of this system of ODE is the span of these functions, which are exponentials in the eigen, with the constants being the eigenvalues, and they're all parallel to the eigenvectors. Okay. Now the question I want to ask right now is, why are these functions linearly independent? Right. So I've written this as if they were a basis. They are a basis for the kernel of the corresponding T. But why are they linearly independent? Any thoughts? Not scalar multiples? Okay. Not scalar multiples is the correct answer when you have two vectors to check linearly independent. But if you have a whole bunch of vectors, remember, linearly independent means if you have a linear combination of them. So these are, remember, all functions now. This means equals 0, and this means this 0, by the way, is very important. The 0 means in the vector space f to the n. So there's an identity of functions. Why does this imply that all the coefficients are 0? So some people said diagonalizable. Okay, that's not really a proof. Somebody said because the vectors, because these v1 through vn are linearly independent. That's true, but remember, that's a different linear independence, right? So someone had this idea that, well, v1 through vn are linearly independent in Rn. Fine. So, right. So remember, these are the eigenvalues. The corresponding eigenvectors are this, and they are linearly independent. We know that, but why does the linear independence of these vectors imply linear independence of the functions? That's what I'm asking, right? So this what statement here is a linear independence in Rn. Why does this imply linear independence of the functions? This is a very interesting question, actually, because it requires you to think about two different notions of linear independence. Does anybody have any questions about the question? So it's a very common source of confusion in this course that people don't even understand why this is an issue. So please ask a question if you're confused by this.
Is it because since V1 to Vn are linearly independent, then if you view C1 E as the weight for V1 to Vn, then C1 E must be 0. And then since E to the I guess T is not 0 at all the time, then C1 to Cn must be 0.
Okay, so you're close. So somebody had this idea that since e to the lambda 1 t and e to the lambda n t are not 0 at all t, somehow what's written below explains what's above. That's not true. I mean, I don't see the argument there. Some intuition is correct. You want to relate these two notions of linear independence. Somebody said the Wronskian. Okay, the Wronskian that's just the answer to the question. I'm asking you, how do you prove this? There is something called the Wronskian lemma that proves this essentially. But I'm actually now asking you, what's the proof? I haven't told you the proof. I mean, I don't expect you to know it. I'm just curious what ideas come up. But okay, it's a very simple idea, actually.
Wait.
Oh, you had an idea?
I wanted to. I believe that, well, you can treat. Oh, never mind. I think it was going after something, had something to. I think it had something to do with the Wronskian, so I just thought, never mind.
Sure. Well, I'm actually going to tell you the proof, which is one line, and it basically proves something close to this Wronskian. Okay, so these ideas, so there's actually a very simple proof of this. So we're not going to use these ideas. We are going to use that these are linearly independent in Rn, right? We're going to use that the vectors are linearly independent in Rn. So what's the proof? Well, maybe I'll erase this idea and write it anyway. So the proof is A. So assume that some linear combination of these functions is 0. Okay, now that's an identity of functions. That's what it means for something to be 0 in Fn, right? These vector valued functions are literally equal. So the idea now is something very simple. If they're equal as functions, they have to be equal at every point. So plug in t equals 0. What happens if you plug in t equals 0? Well, you get C1 e to the 0 is 1. So C1 V1 plus C2 V2 all the way up to Cn Vn equals 0. But now which vector space is this latter equation in? So this first thing was in Fn. Now what I just wrote, where is that happening?
Now it's in.
All
Now
right.
it is in Rn, right?
Yeah. Good.
And then you can easily
but
solve.
now you use that they're linearly independent. Okay. So it's actually quite simple, but it requires this important and subtle idea, which is functions being linearly independent is not the same thing as the vectors being linearly independent when you plug things in. But functions being linearly, but one of the implications is true, right? That if the functions were linearly dependent, okay, somebody asked a question, does it show C1 through Cn as 0 for all t? So there's no for all t, right? So so here's a way to think about it. I'm assuming this statement that actually means for all t this is true, right? So to show something is linearly independent, I just need to show this, right? That if a linear combination is 0, then the coefficients are 0. So now that means I can use a specific t. I can plug in t equals 0 because it's true for all t, right? So certainly it's true at t equals 0. So all I'm saying is that a linear dependence of functions implies a linear dependence of vectors in Rn, which is impossible. Does that make sense? Another way of saying this is that if you have some functions, if you have, let's say you have a bunch of functions, if when you evaluate them, they're linearly independent, then the original functions have to be linearly independent. Oh, I'm sorry. I take that back. That's not true. If you have a bunch of functions that are linearly dependent, then that linear dependence passes over to when you evaluate them at a particular point. And in this case, that's impossible because the eigenvectors are, because at a particular point, namely 0, their evaluations are linearly independent. Okay, does that answer the question? I agree. This is a much stronger thing than t equals 0, but I'm just using it at t equals 0. Okay, so this has some terminology. So I'll just define it because it's maybe used in other courses and it's used in the book. The terminology is well, okay, so a basis x1 t through xn t of kernel of t. So suppose t is equal to one of these. As before, then a basis of functions, so these are all now functions in Fn of kernel of t, is called a fundamental solution set of this equation. This is not a deep definition, it's just a piece of jargon, but since it's used in the book, I'm just going to say it. Okay? So what we proved in the previous theorem is that if the matrix is diagonalizable, then these exponentials that you get, these are our fundamental solutions. Okay, I mean, okay, we didn't prove that the kernel is equal to that, but we proved it contains that, and you can prove that it's actually equal, as we're doing in the course. So this is an example of a fundamental solution. There's a theorem which is referred to a lot in the book, which is sometimes called the Wronskian lemma, which says if you have a bunch of vectors, if you have a bunch of solutions to, if you have a bunch of solutions to a homogeneous system of ODE, then these things are linearly independent as functions if and only if when you evaluate them at 0, are linearly independent in Rn. Okay. So, you know, another way of saying this is that, I mean, if you write this in matrix notation, this is the same as saying that the determinant of this matrix, that's just a convention. It's actually true at any point. You can plug in any number other than 0. So it's not a problem. Okay. If and only if determinant of is not 0. So what we were not going to prove this in full generality. What we proved is that we proved one direction of this for this particular fundamental solution set of exponentials. Right? I mean, we effectively used the fact that they're linearly and that the evaluations at 0 are linearly independent to prove that the functions are linearly independent. Okay, so any more questions about this? Okay, so now what I want to do is I want to address this point. This required the eigenvalues are real. Oh, okay, so there's a question. If the Wronskian is 0, does that imply that it's linearly dependent? Yes, if there are solutions to an ODE, right? So remember, this Wronskian stuff only applies when you have some functions that are solutions to a system of ODE. So this quantity is called the Wronskian. I will say it. Okay, it doesn't apply in in general. There's this very special property of solutions of ODE. Okay, so so now what I'm going to address is what happens if you have complex eigenvalues. So I'll start by talking about a particular example, and then I'll prove the general theorem as I've been doing. Well, let's say you have the system. You have a 2x2 system where I'm interested in finding a vector valued function x so that this is the matrix, right? That's the system of ODE. So now we know how to we know how to try to solve this. Find the eigenvalues, right? So this is the matrix A. So what's the characteristic polynomial of this A? Well, it's determinant of yeah, minus lambda, minus 1, 1, which is just lambda squared plus 1, right? So in particular, I mean, we've seen this many times before. So in particular, the eigenvalues are plus I and minus I. And they have some eigenvectors, which we also calculated before. They're I1 and minus I1, sorry. Oh, I'm sorry, I got it backward. Oops. 1I. I mean, okay, that would have worked too, but anyway. Okay. So now, okay, we're in kind of a situation we've seen before. So these are now vectors in C2, and these eigenvalues are in C, and they're conjugates of each other, right? Now, we wanted to find a solution to this differential equation, right? And our thing that we discovered earlier is that now if you just take exponentials of these eigenvalues and multiply by the eigenvector, then this should be a solution of the ODE. So to satisfies this equation. And okay, let's just check that. Well, okay. What's A times e to the IT 1I? Well, okay, so that's e to the IT times A times this 1I. But it's an eigenvector with eigenvalue 1, so it's I e to the IT times 1I. And that's just d by dt of e to the IT 1I. So that checks out. So even though these are complex, the same reasoning works, right? That you still get solutions to the ODE. And similarly, you get that the conjugate, so e to the minus I t, 1 minus I, also solves the equation, right? So that's nice. Algebraically speaking, nothing really changed. The problem is that these solutions are not real valued functions. So they're not in the space F2 that we defined, right? Remember, F2 is the space of all and okay, infinitely differentiable, right? So this is not these are not functions because they're not even real functions. So we came across this earlier, right, in the second order ODE section. Any thoughts on how to get some real functions out of these anyway? How can I use these? Add and subtract. Yeah, same as what we did before, right?
So you takes the real component, well, take the real part and then the imaginary part, and you can lob off the I, right?
Yeah, so two suggestions. One is add and subtract. The other is take the real part and the imaginary part, and they're actually the same. So let's just see how they work, right? So let's write this equation as t of x equals 0, where t is the usual operator. So now, well, the idea is to observe, same as before, that a sum of these things is also going to be assumed by linearity. Okay, and now the point is this thing is definitely going to be real. Why? Because it's some vector plus its conjugate, right? This second vector here is conjugate of the first one. But let's just calculate it. So what will you get? You'll get that this is I mean, okay, so let me bring in the second line of reasoning here. If you have a complex number and you add it to its conjugate and divide by 2, you just get the real part. And if you have a complex number and subtract it from its conjugate and divide by 2i, you get the imaginary. You don't have to. That's just a normalization. You don't have to divide by 2. I'm just dividing by 2 here to get the real and imaginary parts. Okay. Otherwise, you'd get twice the real part. Does that answer the question? I mean, let me be very explicit here, right? If you have a plus ib plus a minus ib divided by 2, then you get a. Right? So you need to divide by 2 so you don't get 2a. Okay, so if you do this, then what will you get? Well, you'll just get the vector whose components are the real part of e to the pi t and the real part of I e to the I t. Right? And what is that? Well, again, we need a little box. What's e to the I t? Well, it's cosine t plus I sine t. And so I e to the I t is I cosine t minus sine. So these real parts are now just going to be cosine t and minus sine t. Okay, so basically we observed that the real part of these functions is a solution to the differential equation. Now that's one solution. How am I going to find the other one? How do you find another solution? Any thoughts on this? Well, somebody already said it. You subtract them, right? So this is e to the it 1i minus e to the minus it 1 minus I over 2i, which if you figure it out, if you go back to what's written over here, now you take the imaginary parts, you get sine and cosine. Okay, it's the same as what we did for second order ODE. And the summary is, if you have complex eigenvalues, you just take real and imaginary parts. So, okay, somebody is asking me, can you explain sine and cosine again? Yeah, so this came from this Euler's identity or de Moivre's identity. This, if you look back at the lecture on complex numbers, we derived this formula. So this is very important because to take real parts of exponentials, you need this connection between exponentials and trigonometric functions. Does that answer the question?
Can I ask another question? Like,
Yes.
So when you add e to the it 1i plus e to the minus it 1 minus I, like, I don't think here you can cancel out the i's right here, because there is a e to the it.
Yeah. So okay. So I think what you're okay. So okay, I think what you're referring to is the fact that yeah. So you're wondering why this is the real part of e to the it times 1i, right?
Yeah, it's like if in terms of like normal complex values, if you add the conjugate, it is the real part. But here you got like the weight of e to the it and e to the negative it.
Okay, so the fact I'm using here is that a conjugate of a product is a product of the conjugates. That's a fact about complex numbers. So this is a product of two complex numbers, right? E to the it and 1.
Mm-hmm.
Right? So what I'm not taking the real part of what's inside the vector separately. I'm literally taking the real part of this after I multiply it out. Does that make sense? That's why I have an I times e to the it in the second entry.
Okay, so like
I mean, let's just do the calculation since maybe some people are confused. So you have e to the it and I e to the it, right? And I'm adding it to e to the minus it minus I e minus it, right?
Mm-hmm.
Okay. So, and dividing by 2, but let's divide by 2, right? So now let's look inside each entry, right? You get e to the it plus e to the minus it divided by 2, and then you get I e to the it plus, plus minus I e to the minus it divided by 2, right? But the point is, each of these things is the real part of the corresponding entry. There's no problem there, right? The real part, I mean, I'm adding the whole thing to its conjugate. I'm not just conjugating one part of it.
Mm-hmm.
Like the underlying fact here is that the conjugate of A times B is the conjugate of AB for complex.
Mm-hmm.
Maybe that's
so that will say that you just compute both of these real part in one step.
Yeah, the real part of each entry you can compute separately. It's not the same
Okay.
as computing the real part of I and then multiplying it by the real part of. I'm not saying that the product of the real parts is the real part of the product. I'm saying the conjugate of the product is the product of the conjugates. Okay, you can just review your conjugates if this is confusing. Okay, so people are sending me questions privately. It might be best to just send to everybody since they might be helpful. But somebody asked, to get V1 and V2, do you have to do anything special or just use the eigenvalue identity and reduce like normal? No, you don't have to do anything special. They're just eigenvalues and eigenvectors. It's just all you learned in chapter 5. Okay. So this is the same as what we did for second order ODE. It's just maybe a little trickier looking because we're now doing it with vectors. But that just means you do the same thing in every entry. So what's the general theorem? If A is real n by n, has eigenvalues, let's say alpha plus I beta and alpha minus I beta, so they're conjugates, right? And with eigenvectors, let's call them A plus IB, and the bar equals A minus IB. So now, okay, A and B are the real and imaginary parts of the eigenvector V. Right, so these vectors are in Cn, but the real and imaginary parts are real. Then this linear system of ODE has solutions, real part of e to the alpha plus I beta t times V, and imaginary part of e to the alpha plus I beta times t times V. And I mean, you can calculate those. You just use the same identity again. And if you do the calculation, then, I mean, it's done in the book, but I encourage you to do it yourself just to make sure you understand the algebra. You get the following: e to the alpha t cosine beta t times A minus e to the alpha t sine beta t times B. And the other one is e to the alpha t sine beta t times A plus e to the alpha t cosine beta t times B. Okay, so it's just the same idea as we did in the example, but this works in general. That's the point. So nothing scary about complex eigenvalues. Okay. There's still one remaining question, which is what if A is not diagonalizable? Even with complex. So the answer is, I'll tell you it. We're not covering it in the tour course, but maybe I'll mention it at the end of the lecture. There is a way. It's optional. It's super cool, but we won't have time to do it in detail. I'll mention it at the end of the course, at the end of the lecture. So that's complex eigenvalues. That was the first item on our agenda. The second item was inhomogeneous systems, which means equations that look like this. Okay, where again, this is some function in Fn, and x is your unknown. And in operator notation, we want to solve P of x equals f for t, this usual thing. Okay, so I'm actually, we weren't going to cover this in any decent amount of detail anyway. And rather than telling you something very shallow and wasting time on talking about the method of indeterminate coefficients again, I'm just going to make this optional. What that means is the homework from 9.7 is optional, but it's the same idea, right? So the idea is if f is a polynomial. So now I'm going to use this notation. So that means f is some f of t is, you know, a bunch of functions, and each of those things is a polynomial of some degree, m. Then P of x equals f has a solution